Okay, so today we have William Salkeld from Nice, and he's going to talk about lines calculus and coupled Hopf algebras. Please.
Thank you, Karush. First of all, I've had flu for the first half of this week. I think I probably got about an hour's worth of voice, which should be fine for this talk. If I'm losing my voice at the end, I apologize. I'd like to thank Karush as well for inviting me to give this talk. And I'm going to talk for probably 45 minutes, given we've lost the first 50 minutes, about Lyon's calculus and some of the applications of that to studying mean field dynamics. The key idea is going to be constructing a Taylor expansion and then looking at some of the symmetric properties that we associate to that Taylor expansion. And from that, deriving something called the coupled Hopf algebra. Next slide, please. So I'm broadly anticipating we'll cover the first two sections in this talk, and then if we have time, I haven't tested the time on this particularly well, we'll also look at the third section, but I don't anticipate looking at 4 or 5 at all. So next slide, please. Next slide, please. So let's suppose that we have some functional that is defined on the collection of probability measures. So next slide, please. Well then, associated to this measure, we can also construct some probability space that is rich enough that it contains a random variable that has distribution equal to that measure mu. Next slide, please. Then we can equivalently think of our function lowercase u as being some uppercase u, functional on the collection of random variables. Now, there's a lot of technical details there related to finding some probability space that is rich enough, but trust me that such a probability space it does exist. That's not a detail for this talk. So next slide, please. On the space of measures, there isn't really a natural way in which we can define a derivative, but on the space of random variables, we're suddenly dealing with a Hilbert space, and so we can define both the ideas of Gatto differentiability, which we have here on the slide, and the next slide, please. We can also define Frechet derivatives. Now, Frechet being a much stronger sense of derivative than just Gatto in all directions. What we're going to do, thank you, is take our functional lowercase u, lift it to some canonical representation uppercase u, and we're going to show that that thing is Frechet differentiable. Then the Frechet derivative will exist in some dual space, as I've denoted here, which, as this is a Hilbert space, is just isomorphic to this, the space of these random variables itself. Now, the key detail that sort of makes this a good sense of derivative is that this Frechet derivative is measurable with respect to the sigma algebra generated by the random variable x that we that has distribution equal to mu. And so, in fact, we can write it on this different probability space, a probability space determined by this measure mu. So, next slide, please. And so, because it's some measurable function, we can equivalently state the Frechet derivative as being some function of x. And that function is equal to the Lyon's derivative. However, that means that when we apply a Lyon's derivative, we create a new free variable by the application of Lyon's derivative, which could, in the most accurate sense, runs over the support of the measure mu. But to keep things as simple as possible, you can say this free variable runs over the Euclidean variables are d here, but or equivalently over some probability space that we have generated by the lift, this canonical lift. Next slide, please. So let's just look at an example. So typically, the simplest kind of functionals and measures can be some evaluation of the measure with respect to a kernel. So we've got this function f. Now, what we can see when we apply the Lyon's derivative is that we essentially remove an integral of mu and we differentiate the kernel. So you can also see that with this simple example, the Lyon's derivative is no longer dependent on the measure mu. There's no mu on the right-hand side of this derivative of x. However, for more complicated examples, we may well actually have some kind of dependency. The number of Lyon's derivatives you can take broadly is proportional to the number of integrals of mu that you see. So if we go to the next slide, Lyon's derivatives also have quite a natural idea if we're looking natural sort of intuitive sense if we're looking at particle systems. So here we've got this mu, which is the mu bar, which is the empirical measure. Then if we have some function of an empirical measure, and we could take a derivative with respect to one of the variables associated to this empirical distribution, then we get a Lyon's derivative, and then the free variable is equal to the variable that we differentiated in. So next slide, please. So what we're going to be interested in, if we're looking at Taylor expansions, is how we take iterative Lyon's derivatives. Now, the first way in which Lyon's derivatives diverge from classical derivatives is that because we've now got this free variable, we additionally need differentiability in that free variable. So you can see that for the second level derivatives, we now have we can take some sort of Lyon's derivative, and now this has got like a measure dependency and then two free variables, or we can differentiate in the first free variable. You see now this is a function with a measure dependency and a single free variable. Next slide, please. And so let's try and generalize that idea. So to do that, we're going to consider these partition sequences. So let's look at how this definition works inductively. So the first value of every sequence is going to be 1. So A1 is equal to 1. And then the jth term of any sequence is going to be an integer that takes its value between 1 and 1 plus the max of all previous values. So we can see in set A2, we have the sequence 1, 1, and 1, 2. And so this corresponds to, you can sort of think 1, 1 is corresponding to a Lyon's derivative and then a derivative in the first free variable, and 1, 2 is being the two Lyon's derivatives. And we can see that extended through into set A3. And so if we go to the next slide, please, we see exactly that. So now we're able to define these, given some partition sequence, we're able to define these differential operators. And we see exactly the example I just described. Perfect. So next slide, please. So let's also look at what happens when we consider some kind of particle system. So as we've already said, if you take a derivative in some fixed element of this empirical system, then we get a Lyon's derivative, and that variable is the free variable. Now, if we take a double derivative, the second line, we get both this sort of two Lyon's derivatives, and a 1 over n squared, and two free variables. But in the specific case where I and j are equal, we also get a derivative in the Lyon's derivative followed by a derivative in the free variable, and a 1 over n. Now, using this notation here, which is just a way of accounting for the variables, what we see is that when we take some sequence of derivatives for some particle system, we're going to get a sum of all of these different Lyon's derivatives. And the other thing to note is that with this term, when we looked at the second derivative, we could typically, looking at this, it might seem natural, therefore, if you've got some summation over I and over j, it might seem natural that we would partition that into the antisymmetric and the symmetric parts. So now we look at the 1 over n squared and some I and j not equal, and sum these terms when I and j are equal. You can sort of see now these are looking a bit like integrals. So that's quite a natural way to look at this. However, it is important to note that when I and j are equal, we do additionally get a 1 and then we sum over I. We do additionally get a sort of 1 over n and then a sort of double Lyon's derivative with sort of xi and xi as both the free variables. And those terms are going to be of order 1 over n. And as we sort of look at particle systems and take limits, we'll find that those terms are going to be the difference between the empirical system and the mean field limits. And so that's quite a natural perspective to have when you're comparing, say, some differential equation of particle systems, some differential equation in the mean field limit. So next slide, please. So now let's consider a functional that is both on a measure variable and a spatial variable. Next slide, please. Then when we take a Taylor expansion of this, we'd expect that there'd be two first order derivatives. So we'll take a derivative in the spatial variable and a derivative in the measure variable. And notice I've labeled the spatial variable x0, which is going to just distinguish it from the free variables that we obtain by the application of Lyon's derivatives. Next slide, please. And then the second order derivative, we're actually going to get five terms and some idea of joint differentiability, because as you can see, just looking at these 5 combinations, we can swap the order of the spatial derivative in x0 and the Lyon's derivative, but we can't swap the order of the Lyon's derivative and the derivative in the free variable. And that's quite natural if you sort of think about it for a moment, but it means that when it comes to something like a Leibniz type formula, things won't be quite as simple as we might have hoped. So next slide, please. So let's suppose that we have, to sort of really capture that idea of the Leibniz formula for these Leon's derivatives, let's suppose that we have a sequence of zeros of length k, and let's suppose we have some partition sequence of length n. Okay, then what we can do is take some kn shuffle of those two sequences. So concatenate the two sequences together and then take a kn shuffle. So that is just the idea that we need to preserve the order of the sequence A within this sort of shuffled term A prime. Now that would be a sequence of length k plus n, but that's typically not so useful. We'll come to, it's perhaps a useful way to think about these in some contexts, but generally it's more useful to think of sequences that are of length some integer n. And so then we also have this an with a superscript 0, which just indicates that we take all the sequences, subsequences where we consider 0, 0, 1, 0, 2, 0 through to n zeros. Next slide, please. And then similarly, we can also define some differential operators associated with this. And critically, what happens is when you get a 0, you introduce a derivative in the spatial variable, and otherwise find the Leon's derivative as before. So next slide, please. And then what we find is that there's a natural isomorphism between set AN and the collection of partitions of the set of integers. And similarly, there's an isomorphism between the set AN0 and the collection of partitions of the set 0 through to n. So, these two sets of sequences are quite similar in many ways, and also I think it's quite natural to think, instead of as a sequence as such, it's more natural to think of it as a partition of some ordered sequence of elements. So for instance, if you look at if you think of like a classical derivative, then usually the way to think of that is by some sort of multi-index, which broadly represent all the directions, the coordinates that this derivative is considering. And here, I think it's better to think of this as some partition of some multi-index. So we're both going to have a sequence of coordinates, and we're going to have some way of partitioning up those coordinates into subsets. Next slide, please. Yeah, so just for some brief notation I'll probably use throughout the rest of this talk. When we have some partition sequence A, then its length is just modulus, and m of A is just the maximal value of this sequence. Now, the maximal value is very useful because it tells you the number of free variables that you're going to introduce by the application of one of these Leon's derivatives. And we're able to show a Schwartz type theorem, which says that suppose that you've got two partition sequences, and L here tells you the number of elements of the sequence that are equal to I. So LA of 0, for instance, tells you the number of zeros in the sequence. So if you have the number of zeros, ones, twos, etc., in these sequences, and two sequences are equal, then you get that the Leon's derivatives are equal. And this is, again, quite a sort of natural idea for derivatives and is reflected very naturally in the particle system. Next slide, please. And then the other sort of equivalence, as it were, on these Lyon's derivatives is that, of course, the only thing that really mattered here was that I had an ordered collection of elements. So actually what those elements were isn't so relevant, you say. You know, it was natural when we were like, oh, well, we have a free variable x1, x2, x3. But as I've found through my research into probabilistic rough paths and working with post-var, it doesn't really matter specifically how you label these free variables. And so actually, it's quite natural to look at these sequences as actually equivalence classes of all sequences that can be partitioned, and the actual values of the sequence is not important. So next slide, please. And so actually, if you shuffle around some partition sequence, you know, let's suppose that we started with something like 1, 2, 2, and then we could shuffle that around, so then it was 2, 1, 2. Now that's no longer an admissible sequence because the first value is 2 rather than 1. But if we think of these as equivalence classes, then that is actually more like 1, 2, 1, which is a different sequence. And what we found is that you can shuffle around these sequences, providing you also shuffle around the way in which you label free variables, which is exactly what this theorem is saying. You can shuffle the the sequence, and you shuffle the free variables, and everything's just equal. Next slide, please. Right, so let's suppose that we have some smooth function in spatial and measure variable, and let's suppose we've got two measures that have n+1 integrability. This is actually quite a key detail. You can't get it when you're doing these Taylor expansions. You really need to have control of the moments of either of all orders or of one greater than the level at which one takes the Taylor expansion to. Then, I've noticed that I think I probably cut the slide where I defined capital D of A. Please don't worry. This is I would politely suggest this is what you would naturally expect it to be. My apologies for cutting that slide ignorantly in advance. And so we're able to write down these Taylor expansions, and we've also got this remainder term. So if we go to the next slide, please, we can also see the order of this Taylor expansion. So first thing to note was that you're going to have in this first summation, we've got sort of the spatial variables +1, and in the second summation, we've got the sort of integrability of the coupling between measure and nu +1. And so that, that's exactly what we would, as I was describing, right? You need a sort of n+1 integrability to be able to address these remainder terms. Now, when you write down one of these Taylor expansions, you typically make a choice of coupling between the measure mu and the measure nu, and any choice of coupling is admissible, but you pay for that coupling in the remainder term, which is what you can see here. Perfect. Next slide, please. Yeah. So, given all this information, let's try and look at a differential equation. So let's consider this this McKean-Blasov equation I've stated in the top of the slide. Well, if we use this Taylor expansion, then very roughly we could approximate an increment of this McKean-Blasov by the coefficient multiplied by some increment of the driving noise plus some Taylor expansion. Next slide, please. And what we're going to do is then substitute that approximation back into our approximation, sort of again, sort of iteratively. And what you can see we're getting here is some summation of these Lyon's derivatives multiplied by some, again here we've got some iterated integral of increments of the driving signal integrated with respect to itself, plus some remainder term. And this is, sort of following the ideas of both STUs, rough differential equations. So this is quite a natural step to take. So next slide, please. And then we had some first term, which we associated to a node, and then some second term, and broadly that sort of corresponds to a node, and then a collection of labeled nodes directly above that, which are partitioned according to some partition sequence A. And that's going to yield, sort of diffeomorphism multiplied by this iterated integral. Next slide, please. And so then the natural question is, if we keep repeating this, we're going to get objects constructed of this form, and like, what are these? What are we going to get? So that's what I'm going to look at in the next couple of slides. So the next slide, please. And the objects I'm going to be introducing are something that we call Lyon's trees. Now, these require a concept called hypergraph, which I'm briefly going to introduce in this slide. So hypergraph it's a generalization of a graph where each edge can contain more or less than 2 elements. So a hypergraph is said to be d-regular if every node contains exactly d hyperedges, and a hypergraph is matching if the intersect of any 2 hyperedges is empty. So a 1 regular matching hypergraph is one where the hyperedges form a partition of the nodes. And the hypergraphs that we study will have some distinguished hyperedge, which we denote by H0, and will be colored gray, which is the, if you are colorblind, is with the hypergraph on the left, the node contained labeled 3, and on the far right is the node with a label 1. We use this visual convention, and other hyperedges will be colored red, blue, and green. Next slide, please. Let's suppose that we have some labeled non-planar forest. When the hyperedges of the hypergraph that I'm describing, so this n and then h prime, this hypergraph, satisfy these following 3 conditions. You can see 1, 2, and 3 on the slide. And we say that this is a Lyon's tree, a Lyon's tree or a Lyon's forest, because not a unique root. Yes, we have this distinguished hyperedge H0, and when these 3 properties, the first states if the 0 hyperedge is non-empty, then it contains a root. And the second and third property basically give us some something like a geometric visualization of how these hyperedges should be structured on the tree. So if we go to the next slide, please, I think we have some examples. Yeah, so this first example is looking at the first rule. So these following partitions over some trees are not admissible. You see that the gray tagged 0 hyperedge is non-empty, and it does not contain the root. But if we go to the next slide, this example is admissible because now on the left the zero hyperedge contains the root, and on the right, the zero hyperedge is empty. Node 4 is now contained in a blue hyperedge. Next slide, please. For the second rule, I think my internet has just cut out. Going to pause. Hopefully, I'm now connected again. So it's the idea that hyperedges can't jump around another hyperedge. So these two examples are not valid because one on the left, we have two nodes that are on different levels, two different distances from the root, and yet the one that is further does not have its root contained, its root, which here is the node 2 contained in the hyperedge. But if you go to the next slide, please, you can see that these are admissible. If you go to the next slide, we have the third rule. So again, this is not admissible because we have nodes 4 and 5 are contained in some hyperedge. They do not have, they're at the same sort of distance from the root, and they both have a node below them that is not equal. So 5 has 3 below it, 4 has 2 below it, and these two nodes are not equal. And that's not a valid situation. But if we go to the next slide, this example is valid, because this rule is now satisfied. So if we go to the next slide, please. Yes, so I don't think what's on this slide is particularly relevant, so I'm not going to talk about it a lot. But essentially what this says is if I've got two partitions of two sets, and those sets overlap in a good way, then I've got, this is just a way of defining a partition that essentially stitches the two partitions, P, a partition of the set A, and Q, a partition of the set B, get stitched together, forming a quote-unquote good partition. Go to the next slide, please. So let's suppose we have some non-planar label directed tree. Then we can define these sequence of sets. I'll just sort of briefly hit what these sets are. So NX is a node and all of the nodes that are directly above it. N0 is the set of all roots. And then Ni plus 1 is the set of all nodes that are directly above nodes contained in Ni. So that's nodes that are sort of I distance from the root. And N hat is the set of all nodes that have some node directly above them, so not leaves, for instance. Go to the next slide, please. Now let's suppose that for all nodes that are not leaves, that we have some local partition of that node and all the nodes directly above it. So just a local partition. Then what this result is essentially saying is that we can stitch all of those partitions together using this overline union that I described earlier. So next slide, please. What this result is essentially saying is that this was where my notes crashed. Okay, interesting. This result essentially says that if I take some non-planar labeled tree and I have some local partition of it, then I can use that to construct a partition of the whole. Further, if I have a partition over the whole tree, then I can restrict that to local partitions of each node and the nodes directly above it. I can then stitch all of those local partitions together, and I will get a partition that satisfies the definition of of Leon's tree. And if I start with a partition that satisfies the definition of a Leon's tree, I chop it all up into local partitions, and then I stitch it back together again, I will still get, I'll get the same Leon's tree back. And so that is very much the definition of a Leon's tree, as I've described, is this property that you can chop it up into local partitions and then stitch them back together and get the same partition. Next slide, please. Now, given two Leon's trees, we need to define a product between these two trees. What these results are saying is essentially you take unions of nodes, unions of edges, unions of labelings, and you take unions of the zero hyperedge and unions of the collection of all other hyperedges. Well, what does that look like? Let's look at the example on the next slide, please. That's the idea. If you have these two trees, both having zero hyperedge and then some other hyperedge, which I've labeled red on the left and right hand side, then the product is now a Leon's tree with where I've unioned the zero hyperedges, but all other hyperedges have now got a set that contains two hyperedges, and therefore now got two hyperedges, the red one and blue one. Perfect. Next slide, please. We also need this detagging operator E. So E maps a Leon's tree to another Leon's tree, which has, by mapping the zero hyperedge into the collection of all other hyperedges. And we can also pair the operation E with a partition sequence, which is what I've done in this remark. And so the partition sequence very much partitions all of the zero hyperedges by sort of bundling them all together and then mapping those bundles of zero hyperedges into the collection of all other hyperedges. And the choice of the calligraphic E here is because this operation is algebraically similar to expectation, but in a very specific but nebulous way that I'm not going to explain here. So next slide, please. So yeah, you can see in this example, the top one, the zero hyperedge, is grey, and that's matched to a coloured hyperedge. But when there is no zero hyperedge, E does nothing. So next slide, please. And this final operation is rooting, and this is the same from sort of classical ideas of trees and sort of Runge-Kosar type estimates, Combs Primer space, etc. The key detail is that the newly generated root is placed into the zero hyperedge. We see that on the next slide. With these examples where rooting creates a new node, placed when the zero hyperedge is empty, it's then populated. And with this second example, you can see that the zero hyperedge is merely extended rather than creating a new node. Perfect. Thank you. So next slide, please. Now, given these collection of symbols, we're able to define a module that is spanned by these Leon's trees. Yeah, so the first thing to note is that the number of probability spaces we've got in each of these collections of measurable functions is 1 plus the number of hyperedges. Now, it might be natural to think, oh, so that first probability space is associated to the zero hyperedge. That's not quite accurate. So there are lots of times where, for instance, you could consider a Leon's tree where the zero hyperedge is empty, but this probability space is still populated. And then we can further extend these with the multiplication operator that I defined and the decoupling operator, can be extended onto this module. Perfect. So next slide, please. So what I wanted to mention in the last couple of slides is, in this section, is the idea of the elementary differentials. We saw that at the beginning, where the first elementary differential associated to a single node was just the function f. And so we see that here in the sort of first definition, and we're able to sort of roughly see what the elementary differentials for some sort of simpler choices of some Leon's trees would give. And this is an inductive definition that allows us to see sort of in full generality what this is going to look like. And I guess the point I would emphasize is that what we've got here is summing of all possible combinations of partition sequences and some collection of J Leon's trees. And then we are producting them all together according to the those collection trees all together, and then we're rooting them. So this operation very much only sees these elementary differentials are only really defined for Leon's trees, where Leon's trees rather than forests. This is quite natural if we looked at the expansion we had, where the zero hyperedge is non-empty, and that's you see this because so there's I've taken some product trees and I've rooted. So the moment you apply the rooting operations, the moment the zero hyperedge will always be non-empty. Excuse me. Yeah, and you can also see that there's this collection of free variables, which I wasn't going to. There are some key details that I've had to skip over, but you can see as well that there are free variables for each of these objects equal to the number of hyperedges. So the hyperedges are very much corresponding to the probability spaces and the free variables that you'll get by the application of the Leon's derivative. So I've got 4 minutes left, and I don't think that's enough time to really talk about the next section, which is couplings. And so that's, and if Karush wants to go just to the next slide, so you've got the
you can use another 5 or 10 minutes. It's no problem.
Oh, okay. If I've got 10 minutes, I could probably cover this. That's okay?
That's great, yes.
Yeah, okay, perfect. Yeah, so let's carry on to the next section, please. So going down, couplings and couples. So I've described, how we do these Taylor expansions and get these elementary differentials out. And then the next idea I really want to introduce is how we take the associated to each of these elementary differentials is going to be some iterated integral of the driving noise for some specific time increment. And what I want to look at is how we can study the sort of group properties of these iterated integrals. And what we're going to see is we're going to need some way in which the hyperedges, which again correspond to probability spaces, can interact with one another. And the way that they do that is via couplings. This is a natural choice of word because if you've got two random variables, you want them to interact, you need to know the joint distribution between them, which corresponds to a coupling between cores of these two random variables. Excuse me. So let's take us a step back for a moment and suppose we've got two partitions. Then the set of couplings between these two partitions is itself a set of partitions that have the property that when you that are partitions over the union of the two domains of partition, M being the domain of partition P and N being the domain of the partition Q. And so, you know, a set of couplings of P and Q is a set of partitions over the set M union N. And all these partitions must have the property that when we restrict to the set N, we get the partition P, and when we restrict to Q, to N, we get the partition Q. So let's look at an example. Next slide, please. So suppose we've got these two partitions of, you know, M being a set 1 and 2, and N being a set 3 and 4. Then there are three ways of coupling these together. So you can couple the set containing 1 with the set containing 3 and 4, or you can couple the set 2 with the set containing 3 and 4, or you can just not couple the sets together. But critically, we can't consider a scenario in which 1 and 2 are then in the same set, because when we restrict to that, we wouldn't get the partition we have for P. So next slide, please. So let's suppose that we've got two Leon's trees, and we've got, and so that, you know, those have associated to them two collections of hyperedges. And let's suppose that we have some coupling between these two sets, these two partitions. Then and we can define this ordered triple, which is a pair of, give it a moment, my internet dropped out. Sorry, I think that was my internet dropping out. So we have a pair of Leon's trees and a coupling between them. Then we can consider the collection of all such triples, and we call this the collection of all coupled pairs. Now, if we were to restrict ourselves to the scenario where the collection of all other hyperedges was, for instance, you know, the empty set on left and right hand side, then the set of coupling between the empty set and itself is just the empty set. Is only one way of doing that, and so this would very much look like a set of Cartesian products. And you know, so that's natural. If there, you know, there were none of these sort of free variables banging around, this would just be a Cartesian product. But this is a way of describing a Cartesian product that is somehow richer and captures all of the joint distributions that we want to capture. So next slide, please. Oh, I'm definitely going to skip this slide. Let's go to the yeah. So then, what we're going to now deal with is this richer sense of tensor product. So we have this is just again a module spanned by the coupled pairs, and notice now the number of probability spaces is 1 plus the number of elements of the coupling between our two Leon's trees. And you know, that's very much, you know, saying, oh well, when we've coupled these tagged variables together, then we see that in these are now free variables that are equal, and so the number of free variables is essentially smaller. So this is quite natural. But you know, I've used the notation of a tensor product here to emphasize this is like a tensor product, but it's also much richer than a tensor product because we're not spanning by the Cartesian product. This is richer than a Cartesian product. This is richer than next slide, please. Perfect. Now, if we were doing these looking at these trees in a Cones-Primer type setting, then in order to define the Cones-Primer coproduct, we'd be looking at cuts of these trees. Go to the next slide. So a cut is typically some line that goes left to right, passing through the edges. And go next slide, please. What we would get by the application of a cut is a pair of trees, which we call the prune and the root. Now, in this example, notice that there is a red set on the left and a red hyperedge on the left and right-hand side of this product. So that is a visualization to describe that those two hyperedges are coupled together. This is a visual way of writing this. We also see that the grey, the zero hyperedges, are also coupled together in the same sense. Yeah, so the application of a cut here yields a coupled pair. As we go to the next slide, please. So in the same way that we had given some Leon's tree, we can use the same Cones-Krymer type structures to define a coproduct of it. But the output is going to be a collection of pairs, coupled pairs, where the coupling comes from the collection of the hyperedges of tree T. So very much the hyperedges of T tell us how we couple the prunes and roots of this Leon's tree. And this coproduct satisfies these three properties that I've written here. The first two are very natural, and you'd expect these as they're similar, if not identical, to the relationships you see in the Cones-Krymer setting. And this third property just tells you that if you apply the decoupling operation E to the zero hyperedge, then couplings essentially work the same way. There's a tilde here just to capture that the coupling is a little bit. You need to address that there is a coupling, but the way in which it works is perfectly natural, and you get a coalgebra homomorphism for E is a coalgebra homomorphism. So this is quite natural. Next slide, please. Yes, so I've introduced the idea of the coproduct. The final idea I wanted to address is the idea of the antipode, but to justify that, I'm going to introduce a grading. The only thing I think, given I've only got a few minutes left, that I think is worth highlighting is the grading sees both the number of elements in the zero hyperedge and all other nodes. So the grading is over pairs of integers. Yes, next slide, please. And in the same way that in the Cones-Krymer setting, given that the Hopf algebra you're working with is graded, there's a natural antipode. We also get that there is a natural antipode in this setting, but again, you need to capture the couplings going over these random variables, and you see that in this inductive definition that I've stated at the bottom here. But the antipode is very much just the inverse of the identity with respect to the convolution product induced by the coproduct. So this is perfectly natural. Next slide, please. Yes, and so where I'm going with this is that now that we've got essentially something that looks like a Hopf algebra, and we've got a coproduct which isn't going to induce a product, some group operation on the characters on this coupled Hopf algebra. So that's, so we have this first equation one, which is this first property, and this is the property that you would recognize for characters. And we have this second property, which I've stated below. And this is this property essentially captures the idea which is common to McKean-Vlasov equations, which is that the law of the McKean-Blasov equation is independent of the sample of that one specifically considers. So if you would say, oh, let's consider x being my McKean-Blasov equation and look at its coefficients, then its coefficients are dependent on x and the law of x. And the law of x is independent of the sample x. And that's exactly what this property 2 captures. And if we sort of bake that into the characters and go to the next slide, please. Yeah, so at this point, let's skip this slide. This is sort of working our way towards now probabilistic rough paths, which I really didn't anticipate we'd get to. I think I should probably thought of a better conclusion than we got to. I think this slide will be this slide will be a nice concluding slide. Oh no, let's go back up to, please. Yes, this one will be perfect. And so this, what we've seen is, I very much described coupled Hopf algebra and the associated elementary differentials, and now we've got to a definition of the probabilistic rough path, which is a way of giving meaning to the iterated integrals that we also needed to. And yeah, I don't think it's given everything what I wanted to talk about, it's so relevant to talk about this anymore. Yeah, sorry, I didn't have a good concluding point planned for this, I'm afraid. Yes, a probabilistic rough path is very much similar to a rough path in that it's an algebraic object that captures all of the information necessary for a signal to drive a differential equation. A probabilistic rough path captures both the driving signal and the distribution of the driving signal, and that distribution allows you to sort of run in parallel all possible. So it allows you to sort of drive the law of the solution equation. That's the best way of thinking about it. Some distribution for the increments of the driving signal that allows you to drive the law of the solution. And so you have, and it has all of its properties are very much captured by these coupled Hopf algebras. One has to take care in addressing all kinds of integrability details because, of course, when I described these modules of random variables, these were very much collections of random variables without any kind of integrability properties. And that's because the moment you start taking products and shuffling around random variables, it's very hard to retain integrability properties. But what a probabilistic rough path additionally carries all sort of integrability information you need, and you see that in these functionals Q. Yeah, my voice is really giving out now. Yeah, so to conclude, I've talked a lot about derivatives and their properties, and we've seen how those properties build into the structures of coupled Hopf algebras, which I talked about, and those give rise to probabilistic rough paths. And a big focus of my research is exploring how those properties can be used to extract information about mean field equations. I think this is a good place to stop.
Okay, thank you very much. Are there questions?